In this video, I'm going to talk briefly about the data transformation, and then I'll give you one example of that, okay? So in the last videos, we discussed about how do we test the normality of the data, because the normality is one of the main assumptions in the most of the hypothesis testing, okay? If you are testing a hypothesis for mean or the variance in one sample, two samples, the normality of the data is the necessary condition. Although the perfect normality is not possible, none of the data have the 100% normality. But if the data is slightly deviated from the normality, all those hypothesis tests gives you the valid result, okay? But if just in case if the data, if the normality test show a severe violation of the normality, if it is if it is not normal, if it is like very right skewed or left skewed, then how do we try to handle that type of problem is the next thing, which we do the transformation of the data, okay? So the transformation of the data can make the standard deviation more similar in different groups and improve the normal distribution to the data. When sample does not follow the normality, which is true in most of the small sample cases, the transform data may better show the normality, okay? And after the transformation, the test or the estimation will be done for the transform data. So whenever you transform the data, then you will be doing all the problem for the transform data, okay? You will complete the test or whatever you want to do in the transform data, and then you will interpret the result in the original data, okay? The three most frequently used transformation are log transformation, arcsine transformation, and square root transformation. These are the three most frequently used transformation. Okay, let us talk about the log transformation. The data are converted by taking natural log of, so ln x. X is the data set. Whatever data set you have, you will just do ln, take ln on that, or log x, okay? Log x is the base 10, that is a natural common logarithm. Ln x is the natural logarithm. Note that same type of log should be used to transform the data from both sample if there are more than one sample. So if you have more than one sample, the same type of log, either use ln on both data sample or log of both sample, okay? Also, log transformation cannot be applied if the data are negative values. If the data contains 0, you can transform the data as ln x plus 1. So if there are negative values, then you can add a big number on that value so that all the data will transform to the positive values, and then you interpret the result later on, okay? All right, so usually the log transformation is useful in the following cases. The measurement are ratios or product of variables. The frequency distribution of the data is right skewed. In that case, log will help better. The group having larger mean also has larger standard deviation. And the data spans several order of magnitude. In that case, the log transformation is useful. Let us see one example, okay? To test whether the marine reserves are better for biological conservation and the protection of fisheries, scientists calculate biomass ratio, defined as the total mass of the marine plants and animals per unit area of reserve divided by the same quantity in the unprotected area, okay? The biomass ratio would be equal to 1 if the protection have no effect, because the with protection and without protection you will get the same value, so the ratio will be 1. The ratio would exceed 1 if the protection is beneficial, and the ratio the following data is the biomass ratio for the 32 reserves. They found the biomass ratio of the 32 of the sample reserves, okay? So these are the biomass ratio. It looks like most of the biomass ratio in the sample are greater than 1, meaning that the reserve helps for the marine plants and animals. That looks like from the sample, but we want to test that for the population, okay? For alpha equals 0.05, test the claim that the marine reserve is beneficial. So you want to test that, but before that, we want to test the normality. Let us see that. Solution. So h sub 0 mu equals to 1 is the mean biomass ratio is unaffected by the reserve, because that is the ratio, right? And we are testing for the population using the sample. H1 is mu greater than 1. That's what you want to show that, right? Because biomass marine reserve is beneficial for the biological conservation, meaning it will be greater than 1, right? If it is equals to 1, then there is no benefit If it is greater than 1, meaning bigger benefit, right? The mean biomass ratio is better with reserve protection. So before we apply the t-test, because this is the we don't know what is the population standard deviation, so we are testing for the mean. So there are two types, right? One is when sigma is given, that is we use z-test, and when the sigma is not given, we use t-test, right? So since sigma is not given here, we will be using t-test. Before we apply t-test, we check whether the data are taken from normal distribution or not. The QQ plot shows the data not well fit in the straight line, and also the Shapiro-Wilk test implies the p-value is 8.85 times 10 to the negative 5, which implies the population is not normal. Let me see that. So what I want to do first is I want to copy and paste this data in R. Okay, that is A equals to, that is all the data set. So let me run that one. Okay, now let us do the QQ norm. So this is the QQ norm data, and if you do QQ line, so this is what you see. Okay, it looks like there are some of the data are not close to the line, and also on both of the endpoints they are not close to the line. Okay, so but we cannot say that whether the data are normal or not for sure from this plot only. So I want to do the Shapiro-Wilk test. If I do that, I got the p-value is 8.85 times 10 to the negative 5, which is less than alpha. So p-value less than alpha means what do you get? So p-value less than alpha, let me write down that. So p is less than alpha means the data is not normal, right? It looks like it is severely because it is too small p-value, it is severely deviated from normality. So you can say that from here. Okay, that is the Shapiro-Wilk test result from that. Okay, now what I want to do here is I want to change this data by taking log. So in R, if you take log, that means log base e, that is a natural log. If you do log 10, that will be common logarithm. Okay, so I'm taking log a, that is the natural log of a. So this is a values. Now I'm taking b is natural log of a, and if you do QQ norm of v, it looks like it is a little better here, right? If you draw a line on that, see they are close. Previously they were like it was little above, but now they are a little bit close. But we cannot say still whether it is normal or not. What I'm going to do here is I'm going to do the Shapiro-Wilk test, right? So when you do the Shapiro-Wilk, you see that p-value is greater than alpha. What is our alpha? Alpha is 0.05. So p-value is 0.065, that is 0.07 actually. So it is greater than alpha. So it is normal, right? So you can see that here p is greater than alpha. So the data is normal. So the transform data is normal here. Now you can do the t-test for that transform data. What is the transform data? That is b, right? So what I'm going to do here is I'm going to do t.test b mu equals to 0. Why mu equals to 0? Look at this. So after you take log on all those data, you will be taking log on this one too. So log of mu equals to log of 1. So natural log of 1 will be 0. So log of u I denote by mu prime. Log of mu I denote by mu prime. Okay, mu prime equals to 0 versus mu prime greater than 0. You see that? And if you want to do by hand, you do the test statistics, p-value and everything, right? So you see, test statistics is x prime minus mu prime over s prime over root n. That is, x prime is the mean of the transform data. Mu prime is that 0 thing, that 0, right? And then s prime is the standard deviation of the transform data. And then n is the sample size, so root n. If you do that, you get 7.40, and p-value is 1 minus pt, because you're finding the area right of that. That will give, because the right tail test, right? This is right tail test. So you need to find out the area right of the test value. When you do that, you will get very small p-value. That is, we will be rejecting this null hyper, meaning that we will be accepting that. But if you want to do by R directly, what do you get? You get, see, t.test b mu equals to 0, significant level is 0.05, and alternative is greater because it's the right tail test, right? If you do that, what do you get? You get the p-value is very, very small, 1.247. This is for this hypothesis testing, because for the normality we got the p-value already greater than alpha, so we say that the data is normal, so we can use the t-test. And then we use the t-test for that, because before you use the t-test, we wanted to test the normality and the transform data follow the normality condition, right? So do not violate the normality condition. So we are using the t-test for that transform data. That is the idea, okay? See, what we got here is p-value is less than alpha. So we reject the null hypothesis, we reject this one. So hence the marine reserve has a higher, because we will be supporting this one, right? So the marine reserve have a higher mean log biomass than the unprotected area. See, we are saying mean log biomass. Why is that? Because we're taking the log for the data. Okay, now we can find the confidence interval using the transform data, but once you find the interval, you need to change back to the data by taking the e to the x. So if you are asked to find out the confidence interval, because this is the right tail test, so this is the confidence interval. If it was two tail test, the confidence interval, both of them will be the number. In that case, to find out the confidence interval of the original data, you need to take the natural log, exponential. So e to the that and then e to the that, you will be doing that. E and then to the raised to that number, and e raised to the other number will give you the confidence interval of the original data set. Okay, that's what you do. So let me talk about the note here. So log is not the only transformation you use. There are other transformation people use. Okay, so another one is the arcsine transformation. That is, this transformation is used if the data are proportion or percentage. If the data are the percentage, then this transformation is more useful. To transform into the arcsine, we use p prime equals to arcsine and root under p. That's what you do, where p is the proportion measured in a single sampling unit, because that was the ratio. Our data here was ratio, right? But sometimes the data are proportion like 0.1, like less than 1. Okay, in that case, arcsine will be more helpful. That's what it is saying. Okay, and then square root transformation is, by the way, where p is the proportion measured on a single sampling unit. Note that if the original data are given in percentage, you need to change them into the proportion by dividing by 100. That's what it is saying. Okay, next is square root transformation. Square root transformation are used if the data are count, such as number of mates, eggs, etc. So that is x prime. This is the formula you use, the square root transformation. X prime equals to x plus 0.5. Like a log transformation, sometimes it helps to equalize standard deviation between groups when the group with higher mean has higher standard deviation. Okay, note there are other type of transformation, such as square transformation, x prime equals to x square, anti-log transformation, reciprocal transformation, etc. Okay, so this is the square transformation, this is the anti-log, that is e to the x transformation, and this is the reciprocal transformation. So you can try any of these transformation whenever you try to test the normality, and then if it violates, if it shows that the data is not normal, then you can try one of these transformation. And if one of these transformation shows that data is normal with the transform data, then you can work with that data, take that data, transform data, and then test the hypothesis. Okay guys, so this is how you do the data transformation. Now what if the data is not normally distributed? Suppose that you tried all those transformations, everything you tried, but it still shows the data is not normal. Then what do? Transform the dependent variable, repeating the normality checks on the transform data. Common transformation include taking the log or square root. So you transform that is the first thing you do. Okay, if it still violate, then use non-parametric test, which is the next chapter. Okay, you will be using the non-parametric test. Non-parametric tests are often called distribution free test and can be used instead of the parametric test. So in that case, we will be using, if all those methods shows that the data is not normal, then we will use the non-parametric test, which is basically used for the data set that violates the normality. Okay, use a parametric test under robust exception. These are conditions when the parametric test can still be used for the data which not normally distributed and are specific to individual parametric test. Sometimes you can ignore the normality assumption if it is not much deviated from the normality. If it is like close to the normal, then you can still use. Okay, I will post the homework together with this one. There will be other homework too, so I will post the homework separately. Okay, so this is how we handle the non-normal data. Okay guys, thank you.